Good morning, ladies and gentlemen. This is Ben Keyser with Applied Flow Technology, and I want to thank each and every one of you for joining me in my webinar today. I'm excited to let you all know that today is my 7-year anniversary with AFT, and I absolutely love it here. And it's been a wonderful experience to be able to work with and serve all of you listening in over the years. And thank you for any of your tech support questions that I've been able to help you with, or just any of your phone calls or emails that I've been able to help you out. And here's to another 7 years, hopefully. Uh, so today's a great day. Anyway, I'm excited to talk to you all today about fire suppression and how to model that in our software. And I don't have any slides prepared today because I'm going to basically be showing everything in the software itself. So before we get started, I want to point out a couple of things. One is just where you can find information about all of our different AFT products. If you go to our website, aft.com, under the products menu, you can go to our software overview, and that'll give you a very high level description of each of the tools that we offer. And then if you click on any of them, it'll take you to that specific product page to where you can get some more details on that. In addition, I want to let you all know that we have our training seminars for AFT Fathom, AFT Arrow, and AFT Impulse coming up here in a couple weeks. They are going to be in the first week of October, and you can register right here on our website. So Fathom is October 1st and 2nd, AFT Arrow is 3rd and 4th, and then AFT Impulse is the 3rd through the 5th. And if any of you are ever able to make it out to Colorado Springs for a visit or a training seminar or anything, be sure to stay a couple extra days out here. There's a lot of beautiful things to see and do in a very close proximity. So when you're out here for training, make sure that you get a little bit of sightseeing time in as well. A few other areas that are important is our blog page. If you go to the About menu, find our blog. We have all of our articles that we write in this area. We have 3 different categories. There's the President's Perspective, that is the blog that our President Trey Walters writes. And then we have our Tips and Tricks articles area that is huge with tons of articles that all contain useful tips and tricks on how to use our software more effectively and efficiently, and a lot of them come from common technical support questions. So if you're running into trouble on anything, go to our tips and tricks page. There's a very good chance that we would have written an article about what you're dealing with already. And then finally, there's a events blog area where right now, one of the main events that we are participating in is the Pump and Turbo Symposium down in Houston, Texas. And so if you are at the Pump and Turbo Symposium down in Houston, be sure to stop by our booth if you have a chance. A few other areas, you all know where you can register for upcoming webinars. But I want to point out our webinar library. If you go to our webinar library, then you can fill out the form of information here. And this is how you'd be able to access all of the previously recorded webinars that we've done in this area. And so there's a lot of good content in there that you can learn more about how to use the software more effectively and efficiently. Lots of good stuff on our website. That's about all I'm going to cover before we get into it. So if you haven't done so already, make sure you check out different areas of our website. There's a lot of information that you can find there. Okay, so today I'm talking about fire protection and sound suppression using AFT Fathom and AFT Impulse. And so AFT Fathom has had the ability to model fire protection systems for a very long time, and it's been able to do all the various hydraulic calculations that you would need to do in order to stay within compliance of the NFPA codes 13 and 15. AFT Fathom has been able to use the Hayes and Williams factors that you would use often in fire protection. And so nothing is new in terms of doing the fire protection calculations inside the software themselves. And so I'm going to start off with this very simple example. This is just found out of one of our example help files. So, excuse me, if you go to the help menu while you're in Fathom, and then there's show examples and choose your desired units, the example that I'm going to give a high-level overview of is the spray discharge system. And so in this system here, I have a series of spray discharge nozzles that are spraying water and hopefully putting out those fires. And so what the goal here is you need to figure out what supply pressure you need in order to ensure that you have a minimum flow rate of, let's say, 100 gallons per minute through each spray nozzle. And so if I open up one of the spray nozzles, you can see how it's defined. I have it specified as a using the discharge coefficient for my spray nozzle geometry. The exit pressure that you have to define, this is simply the ambient pressure conditions that you are discharging into. So if it's atmospheric, then it's going to be 0 psig. After you specify that, the next thing that you would have to enter is the discharge coefficient. So, a common one is 0.6, and then a discharge flow area. That's the size of the hole that you are discharging through. We do have a few other models available. There's a Sparger model, and that's where you would specify the flow area of one hole, and then you can specify how many holes are. Think of a shower head. That's what the Sparger would be like. And then we also have a K-factor loss model. For the K-factor loss model, you would specify a K-factor right here. But the one thing I want to point out is that if you use the fire sprinkler option for this loss model, it's not the standard K-factor that you would see in the delta P equation for delta P equals your K-factor times 1/2 rho V squared. It's not the same K-factor. This is a special K-factor that has units with it. And so if you click on the help menu for the loss model, you can go to the K-factor. This is the equation that's being used for that fire sprinkler. So it has units, and the units are volumetric flow rate, gallons per minute per square root of PSID. So those are the different loss models for your spray discharge nozzles that you can work with. So I'm going to go ahead and run the model, and I'm going to see what pressure I need in order to get the required flow. So if I run my model here and I go to the output window, the important parameter that I'm interested in is the flow rate through the spray nozzles. So I'm going to collapse the general section and the piping section results. And if I focus right on here for the spray discharge, here's what you'll find. We list the flow rate through one spray discharge nozzle and another spray discharge nozzle. But why is it that we have not applicable for all the rest of the other spray discharge nozzles? Why can't it calculate the flow rate through those sprays? Well, it can, but here's the thing, is when you're flowing into a spray nozzle, hope you all enjoy my beautiful artwork, you have two outlets through a spray. So you have an outlet which is coming through the spray nozzle itself, and then you have a outlet into the next pipe. So when you use the word through, volumetric flow rate through the junction, which through are you talking about? Are you talking about the flow rate through to the next pipe, or are you talking about the flow rate through the spray, or some combination of them? Well, the answer is it's ambiguous. So there's no answer for that. So here's what you have to do in that situation. You have to go to the output control window right here. This is where you could specify which output parameters are being displayed. These are the list of available parameters for pipes, and then this is the list of parameters that are actually being displayed. So if I go to the junctions parameter, there's a special parameter which is what you would be interested in for the spray nozzle. It's called either mass flow rate net at junction or volumetric flow rate net at junction. So it's the keywords net adjunction that you need. When you are interested in figuring out what is the spray flow rate that's coming out of the nozzle itself, it's the volumetric or mass flow rate net adjunction parameter that you have to add to your list of displayed parameters. So once I add that in, you can now see that there is a values for all of the volumetric flow rates through each spray nozzle. So here you can see they're all between 50 and 70 gallons per minute. So what do you need to do? Well, you've got to boost up your supply pressure to try and get more flow. Now let me erase those drawings here real quick. An easy way to display your results is on the visual report. And with the visual report, this is where you can show your results right on top of the model itself. So when I click on show, there's my results right there. So here I can see that my flow rate is varying in this fashion. The highest amount of flow is going to be in the closest spray nozzles, and the least amount of flow is at the very end. That's where you have the highest frictional losses. So those are your two hydraulically most remote spray nozzles, and those are the ones that you need to focus on in order to determine what supply pressure you need for that minimum flow. So it's just a very basic iteration process. You just open up your, well, actually what I'm going to do is this. I'm going to take my visual report, I'm going to dock it below, and then I'm going to go back to my workspace and show him above, and that way, here's what I can do, is I open up my spray discharge nozzle. Let's go up to 100 psig. Let's try that. So when I go up to 100 psig, I rerun my model, and I go back to my visual report, and there's my new flow rates. So as you can see, you're getting more flow. You're almost to that minimum 100 gallon per minute through the first two spray nozzles, but your outlets are only at 60 or 76 gallons per minute. So we got to keep iterating on that supply pressure junction there. All right, so I'm going to boost up the pressure again. And the pressure that I'm going to try is 200 psig. So I'm going to try 200 and see what kind of flow rates that gives me. So I rerun my model here, and I go back to my visual report. Well, now I'm getting over 100 gallons per minute. So I know that 200 gallons per minute will do it, but it's more than what you actually need. And so what this assigned pressure junction is representing is a pump, essentially. It's a way of simplifying your model so that all you need to focus on is essentially your pump discharge pressure. Okay. Erase my drawings there. I'm going to show one other value on there. I'm going to show my volumetric flow rate in pipe 1. Here's a really cool new feature in Fathom 10 is we have redesigned the visual report to make it a little bit easier to see what you're doing. And so we've color-coded each of these columns so you can see what you're showing data for or what you're not showing data for. So here's what I want to do. I'm going to click on pipe 1, and the next thing I'm going to do is I'm going to invert my selection. The reason why I'm doing that is because I want all of these pipes to be selected. I don't care about the flow rate in those pipes. So I select all of them, and then I uncheck this box right here for data to toggle off the data for those pipes. That way I'm only showing data for pipe P1 right here. That's the only thing that I care about. So that will tell me what my total flow rate is. So here I've got 939 gallons per minute total through my system. So let's ratchet down the flow a little bit. Let me try opening that supply pressure junction here. Let's try 175 psig. Click OK and rerun the model. Go back into the visual report. And as you can see here, you're at 101 and 101. We're getting very close. The actual final answer for this problem is 171 psig. So if you do 171 PSIG, and then for my visual report, I can show more digits for my results here. That way we can get as close to exactly 100 as we can. Rerun my model. And here's my visual report. Things are a little bit cluttered up because I added more digits. So yes, now I'm getting exactly 100 gallons per minute essentially. So 170 to 171 PSIG is your answer. So that's the very simplified method of being able to model a spray discharge system. And it's doing all the straight hydraulic correlation calculations. In this example, in my pipes, what I'm using is absolute roughness as my friction model. So here I'm not using Hayes and Williams. Now, what I'm going to do is I'm going to switch to another example that's a bit more complicated. So let me open up my next model here. Okay, so while this is opening, the reference of where this piping system comes from is from the NFPA 15 code. So if you were to buy NFPA 15 and go to very close to the end of that standard, you would see a piping system for a fire network that looks a lot like this. And we actually built a model of that system. And so here's your spray discharge nozzle network. The same concept, that I covered in the previous spray discharge nozzle is what I would be using in this system. I would go in here and I would change the supply pressure until I get the minimum flow rate for all my spray nozzles. Now here's the thing, this is a much more complicated system. In the previous system, it's very easy to see that my two outlets on each side were the hydraulically most remote spray nozzle. But in this type of system, what spray nozzle is hydraulically the most remote? Is it this one or that one? Or maybe would it be potentially these two right here? Well, it's very difficult to figure that out. And the thing is, you cannot tell just by looking at it. So this is where, if you're doing things by hand, you're going to have to do a lot of extra calculations to go in and figure out which spray nozzle is actually hydraulically the most remote. The reason why is because your piping diameters are changing throughout the system in different ways. Your pipe lengths are changing. You've got different fittings and losses in there that you have to deal with. So there's a lot more complication that makes it more difficult to figure out what you actually have. So here's what you would do in order to model your spray system to remain compliant with the NFPA fire protection standards. The first thing you do is build the model. Well, we've done that. That's finished. And so as you can see, all my pipes and junctions are defined. The next thing that I have already done is I went into the analysis menu, and then under extended options, I turned on equivalent lengths. The reason for that is because fire protection systems deals a lot more with equivalent length method for accounting for minor losses rather than using the standard K factor methods. So this is where you can turn on equivalent lengths. That has an impact on a couple of things. One is if you open up this valve right here, after you've turned on the equivalent lengths, there's a new loss model that's available right here, and that's the equivalent length. So you choose the equivalent length. The next thing that you would do is you would click on the drop-down menu here, and you would look for the appropriate valve that you want to use. Maybe it's a butterfly valve, or perhaps a gate valve, or a swing check valve, and that will tabulate what your equivalent length values are. Now here's the important thing is these equivalent lengths for the standard methods on the drop-down menu They are very specific values that comes from a table that does not have a lot of options. So make sure that if you're using that option that you fully understand where those equivalent lengths are coming for and how to use them appropriately. So in this particular model, instead of doing a standard model, we're doing a user-defined, and the user-defined equivalent length is 41 feet, okay? So that's one impact that the extended options will have on your model. Here's the other impact, is if I go to the model data window, this contains a tabular format for all of my input information. And as you can see here, I am using additional fittings and losses in my pipes, but not in all of them. So let me open up one of these rows here. If I double click on this row right here that has 58 extra feet of equivalent length, it's a 17-foot long pipe in reality. So geometrically, this pipe is only 17 feet long. However, the pipe has additional fittings and losses. So when you turn on that extended options from the analysis menu, your fittings and losses window changes. So here, these are the different types of minor losses that you can lump in to your pipe itself. So what you would do is you would just type in how many fittings you have for each of those types, and then it's going to calculate what your equivalent lengths would be. And overall, there's an additional equivalent length of 58 feet that would account for extra pressure loss in your pipe due to those fittings. So if you are using the equivalent length methods in this fashion, your fittings and losses window changes accordingly. All right. Now, the next step that I've done, as you can see here, I'm using a Hazen-Williams factor for my friction model. So if I was to open up one of these pipes here, what you would see is a user-specified friction model. When you choose user-specified, you can go in and you can pick from this list, and I'm doing Hazen-Williams, and I specify a value of 120. Now here's the thing, I did not go in and specify what the Hazen-Williams factor was in each of these pipes. Instead, there's a much easier way to do it. And you actually have to do it the way that I'm going to show you if you want to do the NFPA report calculations. So in order to do your NFPA reporting, is you would go to the Tools menu, and then you would go to the User Options. Once you go to the user options, this is where you can specify all the different preferences that you want to work with. Font sizes, grid sizes, things like that. But for this particular model, I want to go to the NFPA configuration. I'm going to click on this checkbox right here to enable the NFPA calculations. This will specify a default Hazen-Williams factor of 120 and a default atmospheric pressure. You can change those values in that window if you want, but you don't have to. So after you take that step to enable your NFPA, you would save and close. And then the next thing that you would do is you would go back to the analysis menu and see how now you have a NFPA configuration option, and we're going to use the NFPA configuration to do the NFPA report. You'll see what that looks like here in a couple minutes. The next thing that you would have to do is you have to select a NFPA group. Well, obviously there's nothing here, and so there's two more steps that we have to do before this. One is you would have to go in and figure out which spray nozzle is hydraulically the most remote spray nozzle in your system. While I'm talking about that, I'm going to bring up that code and standard here really quick. So give me just one quick moment here. In order to figure out which spray nozzle is hydraulically the most remote, there's a really easy way to do that, and it's to use the goal seeking control module. So the goal seeking control module will automatically iterate on that supply pressure for you in order to calculate what your minimum flow rate needs to be. Now, give me just one moment here. Let's see. I want to show you the standard of what that actual NFPA report looks like. And so I'm just trying to find where it is here on my computer. Bear with me. Let's see. Give me one moment here. Okay, I've got it. Okay, so while that PDF is opening, this is the report that I'm talking about. And so if this is NFPA 15, all right? So if you go to very close to the very end of NFPA 15, here's the spray nozzle system that I'm modeling, and the NFPA report or the NFPA standard requires you to do your hydraulic calculations in this type of reporting format. And so what you have to do is you have to first find where is the hydraulically most remote spray nozzle. Once you find it, you would start at that spray nozzle. Let's say it's this one right here. And then you basically do all the pressure loss calculations and you work your way backwards to the source of the system. So that's what we're going to do in Fathom. Fathom's going to make that extremely easy for you. So let me go ahead and show you how you would do that. So in order to figure out what is the hydraulically most remote spray nozzle, we're going to use the goal seeking control module. So the first step is to click on this button right here. We're going to turn on GSC. Once I turn on the goal seeking control module, I click OK, and that will close out for me. Next is I go to my goal seeking control manager. Here's where you define your goals and variables. So the variable is easy. My variable is simply going to modulate the assigned pressure value to whatever it needs to be to maintain a minimum flow rate for all my spray nozzles. Now here's the thing. For my goals, I don't want to go in here and do a spray discharge goal for every single spray nozzle like this. That's going to make it, very difficult. I've got, almost 30 spray nozzles in my system. There's a better way. So in order to do that effectively, you actually have to create a group, okay? So what I'm going to do is I'm going to go to the edit menu, and I'm going to do a select special, because what I want to do is I want to select all my spray discharge nozzles on the workspace. So if I click on this drop-down menu to select things in a special way, I'm going to select by junction type. So when I click on spray discharge for my junction type, it selects 28 spray nozzles out of all 72 junctions on the workspace. When I click OK, they're all selected. Perfect. The next thing that I need to do after I select all my spray nozzles is I go back to the edit menu and then I go to groups and I'm going to create a group. This group is going to be called spray nozzles. When you create your group, you'll see the name and then you'll see your certain spray nozzles checked off. You can toggle other pipes and junctions on and off to be included in that group if you like, and then click OK. So once you have that group defined, then you can go back into your goal seeking control manager, and I'm going to do my variable on the assigned pressure junction. Therefore, the goals, when you create a group, there's a new goal type that's available, not just point goal or differential, but there's a group goal. So this is how I'm going to do it. I'm going to click on group, and I'm going to do a group max min. So this is where the group has to achieve either a maximum or a minimum value of a certain parameter. So here they have to meet a certain volumetric flow rate, which has to be greater than or equal to 42 gallons per minute. And then you specify your group. So the group is going to be my spray nozzle group. Easy enough. You click OK, turn on the GSC calculations. If you zoom in, you'll be able to see beside this label right here, for the assigned pressure, that there's a V. That little V there indicates that you have a variable for that junction. Now, typically when you're using GSC, you would also put a G next to the pipes or junctions that have goal specified. But when you do a group goal for more than one component, it's not going to do that. So that's why we have a V but no G's. Okay, so I've got my goal seeking control turned on. Now I'm ready to run my system. So it's going to change that pressure to give me a minimum flow rate of 42 gallons per minute out of every spray nozzle. Really quick before I run the model, here's the way that I am specifying my spray discharge nozzles. I'm using the fire sprinkler option. So if I open up one of these rows here, it's using a fire sprinkler K factor of 3 gallons per minute per square root of PSID for several spray nozzles, and then for a few other ones, so you're using 3 for some and then 9 for others. So that's what we're using. Okay, run my model here, and it says there is no NFPA group defined. Please select an NFPA group. Well, here's the thing. The NFPA group is what you're going to generate that report for. Okay, that report, which is going to look like this. But you have to know the most remote spray nozzle, and I don't know that yet. So what I'm going to do here is I'm going to go to my analysis, and for NFPA configuration, I'm going to ignore that. So that way I'm just doing the hydraulic calculations to figure out the most remote spray nozzle. So I run the model here, and look how quick that goes. It takes just under 6 seconds in order to vary that pressure to get the flows that I want. So I click on output. Now, if you want to do it the manual way where it's a little bit more difficult for you, you could still accomplish that fairly easily when you're only having to change one parameter. So what you would do is go to your spray discharge nozzle junctions, and you can see how you've got your volumetric flow rate through junction, and you can use the sort table by in order to sort that table in ascending order by volumetric flow rate. So this will order your spray nozzle, so you can see you are getting at least 42 gallons per minute through every spray nozzle. Through some of them, you're getting a lot. Through some spray nozzles, you're getting between 900 and 120 gallons per minute. So that's a lot of flow. But you don't care about that because all you're trying to do is what's the most remote. So if I was doing manual iteration, I would sort my results in this way, figure out which one was the minimum, and then make sure I get that number to be 42 gallons per minute. But when you use GSC, what might take you 5 to 10 iterations by hand, GSC will do it in 6 seconds. So here I go to my GSC variables, and this tells me my supply pressure has to be 329 PSIG. That is your pump discharge pressure, perhaps. So if you need to get all that flow, if you've got a whole fire inside that entire building, then in order to get those flow rates to meet the minimum requirements, you're going to need a pump that can deliver 330 PSIG as a discharge pressure. You also would know what your flow rate through the pump is. So if you right click and hold, you can see that your total flow is just under 2,000 gallons per minute. So you got 2,000 GPM, and then your discharge pressure, you can use that to find a pump curve. But if you click on the GSC Goals tab, not only will it tell you that your minimum value of 42 gallons per minute was met, this is the spray discharge nozzle that is the exact hydraulically most remote spray nozzle. So it's J9. Okay, J9 is our most remote spray nozzle. So now I go back to my workspace and I can do Control F on my keyboard to find where J9 is. So that's J9. That's where my most hydraulically remote spray nozzle is. Here's the next step. I have to now create another group for my NFPA report flow path. As I mentioned, the report here starts at the very end of your system and works the way backwards to the supply. So you have to select a flow path. So I'm going to hold the control key down. I'm going to select pipes and junctions that are in that continuous flow path. The thing is, you just have to have the pipes being continuous. You don't have to select the junctions. So I've got that, and I go all the way back to the source. So this is my continuous flow path. Once I've selected it, I go to the edit menu, and then I create a second group. Oops, not select, I meant to click on create. I clicked the wrong button, so click on create. This is going to be called NFPA flow path. Okay, so now I have two groups, all right? So once I get that second group on there, now I go back to the analysis and I go to NFPA configuration and I click on use, because now I want to generate that report based upon that flow path. The last thing that you have to do is go to the tools menu and then click on select NFPA group, and then you have to select which one you're going to generate the report for. Well, you're not going to do one for spray nozzles. That's just all your nozzles. It's not going to get a report because your report has to be a continuous flow path. So I'm going to use this one that I made for that path that's selected in red. So now I rerun my model here, and it does the calculations. And once I get to my output window, I now have a new tab, NFPA report. So this NFPA report contains all of the parameters and values from the calculations that you would need to do to meet your NFPA 13 and 15 requirements. So this is how you're able to calculate your hydraulics of your fire protection system, and then also generate your report to show that you are meeting code compliance. And so that's what the code requires. But when you have a tool like Fathom, I mean, here's the thing. You know, you can generate that report all day long, but that's one spray nozzle, okay? That doesn't mean very much, because if you have a fire on this whole second level, that single spray nozzle is not the most important one. So you've got to make sure that all the other spray nozzles are getting enough flow also, and you want to see how much they're getting. So that's why it's important to use GSC. It'll help you figure out what your total hydraulics will be for your system there. Now, if you don't remember how to do all that, that's fine. Don't worry. Because again, if you go into the help menu, this is another example that's in our examples help file, NFPA firewater system. If you go through this example help file, it'll show you how to build the model, or well, it starts you off with a pre-built model, or you can build it from scratch if you want, and it walks you through the full model definition process, and that will help you learn how to calculate that report. If you want to use the GSC portion to make it easier, there's a GSC example for that as well. So that is how you would do the fire protection calculations using AFT Fathom. Okay, so now I'm going to shift gears and I'm going to talk about how you would do a surge analysis for a fire protection system in Impulse. Okay, if you want to learn more about GSC, if you go to our webinar library, AFT Fathom, 2 weeks ago, I did a webinar on the goal seeking control module and extended time simulation modules in depth. So that's where you can learn about the GSC module there. If I go back to my webinar library, if you want to learn more about Impulse, you know, this webinar is not to focus on Impulse, it's just to highlight one thing. But if you want to learn more about Impulse, you can go to our Impulse webinar library, and you can see a lot of useful information there. And then our upcoming webinars, basically throughout the whole rest of the year, our webinars are all focused on Impulse. So October 3rd on that Wednesday, we're doing an Impulse introduction. We're doing another webinar on mitigating surge issues. pulsation control, waterhammer and surge suppression, etc. So the whole rest of the year's webinars is going to be focused on Impulse. And we're probably going to be slipping in a Impulse 7 new features webinar once Impulse 7 is released here in the next month or two. Okay, so in our blog page, I want to point out our President's Perspective, Trey Walters. There's a particular blog article that I'm interested in showing you all, and it's this one right here. Well, no, not that one, I'm sorry. This is all of his articles that he's written. The one I want to show you is this guy. And so I'm trying to drag it over. There we go. Okay, so this is an excellent blog that he wrote about NASA and their sound suppression systems. And I myself had the pleasure and the opportunity to go to NASA last week, actually, and I just got back from my trip to NASA where I got to teach them AFT Fathom and AFT Arrow. And so I'm going to show you a quick picture. This is pretty cool. This is me right here in the middle, and this is all of my attendees in my Fathom and Arrow class at NASA, and we are standing in front of the vehicle assembly building. So when they're building the rocket ships and stacking them on top of each other, that's the big, giant, tall building that they are building it inside of, and just very, very fascinating. I did a lot of tours there, and it was incredible. But Trey wrote a really good blog, and I'm going to show his article now because he got some, slightly better pictures because he was able to get a little bit closer to the launch pad than I was able to. So when he visited NASA back in 2013, he was able to get right up to the launch pad. This is launch pad 39. This is where the space shuttle would launch from. And where's my pen? The tank right here, this tank is supplying water for their surge suppression or their sound suppression system, because when the rocket ship takes off, there's a whole bunch of hot fire burning from the rocket ship, and it's very, very loud. And so they have to suppress those sound waves because that can damage the ship, and it's bad. So they supply water, and they flood the launch pad with tons of water in order to suppress the sound waves. And so his article talks about that, and it's really cool. And so if I scroll down here, he's got some better up-close pictures. SpaceX owns Launchpad 39A now, and so we weren't able to get close inside the fence. So these pipes here are gigantic. And so this is a video that I want to show really quick here of the sound suppression test that they did on that launch pad. So they start flooding the pad, and then the rainbirds, they dump a whole bunch of water onto that launch pad to suppress the sound waves when the rocket ship is launching. There's no rocket ship there right now because this is just a test. So that is so incredibly amazing. And those rainbirds, they can discharge a total of up to about 900,000 gallons per minute of water. It's amazing. And so that wouldn't really be a Fathom XTS thing. That would be more of a Impulse thing because A, it's happening in a very, very short amount of time. B is you're going to have to deal with waterhammer. There's pressure waves that are going to be bouncing back and forth. And so it's really important to use Impulse to model that type of behavior. So that's their sound suppression system. Now, there's a couple of excellent case studies that were done by Impulse users. Oops, I need to pause that again. There we go. Done by Impulse users, and you can find these right here in the blog article. And this talks about how these companies modeled their spray discharge nozzle system. And so they've got all the rainbirds in there. They're using Impulse to make sure they are getting the right amount of water and making sure that they don't have any pressure issues. Also, they have to model failure cases. What happens if a valve slams shut or if a pump trips? Things like that. So I'm going to show you an Impulse model now. And let me get that out of the way. Okay, so here's a slightly modified, simplified case that I made from that case study. And so here you have a whole network of different areas of the spray nozzles. And so if you read that case study, you'll learn more about this system. So you've got, several different networks of spray nozzles all throughout. There's lots of different transients going on. These valves are popping open instantaneously. These spray nozzles are coming on at different times. And so in Impulse, when you have so much transient phenomenons going on, if you go to the Model Data tab, you can go down to, I'm going to collapse these sections here and show the junction section. There's a transient data section right here. This captures all the transients that are defined in this model. So as you can see, there's a whole bunch of them. So let's look at a couple of them, for example, here. These valves are designed to, they are initially closed, and they're going to pop open very quickly in order to start allowing flow through the system. So that's the transients on the valves. The spray discharge nozzles are also initially off. And so as you can see here, the spray nozzles are closed, and there's a transient set to instantaneously open those spray nozzles to allow flow through the system. Now, here's the interesting thing that you have to be creative when you're dealing with impulses, because initially there's no flow through the system. The whole system is off, and Impulse is going to assume liquid full pipes all throughout the entire piping network. So you have to do some trickery to obtain an initial solution for your pressures all throughout the system when there's no flow. And there are some tips and tricks on how to do that. I'm not going to go into that right now because that's a whole separate conversation. But one of the things I want to point out is using Impulse. It's easy in terms of the interface, but when it comes to the nature of how you define your transients and how you evaluate your results, it's a lot more difficult than it is Fathom. And so it's a lot easier to misuse Impulse in the wrong way than Fathom is. You have to make sure that you get the appropriate level of training. So if you're an Impulse user and you've not been to our training seminar yet, make sure that you highly consider coming to our training seminar for AFT Impulse, or have us come out to train your team of engineers, because waterhammer modeling is very much a gray area. It's not black and white. It takes a lot of careful interpretation to really learn and figure out what's going on. And that's where you have to learn the tips and tricks on how to model this system appropriately to get an initial solution. So I've already ran the model and I've got results. Basically, long story short, everything's off, and then we're turning everything on very quickly, and we're flooding the launch pad with tons of amounts of water. So I already have output results. I have a whole bunch of warning messages. I am not too concerned about these. This is about variable resistance. If you go to our blog page for our tips and tricks articles, I actually wrote a blog about variable resistance a few years ago. So if you do a search for variable resistance, then that should help you be able to find the blog article. Well, look, it's that top one right here. So if you read this article, it'll tell you what all those warning messages mean and when they are, when you need to worry about them or not. Okay, so I've got results. What I want to look at is let's take a look at some flow rates here. And so what I'm going to do is I'm going to plot the flow rate for these 5 spray nozzles. So junctions 143, 145, 147, 49, and 51. So I'm going to go to my graph results window, and on my transient junction data, I'm going to plot those. So we got 139, 41, 43, 45, 47, and sure, that's good enough. And so I'm going to plot the volumetric flow rate. This will show you how the flow through those individual spray nozzles increase over time. So as you can see, once the transient simulation starts, the rainbirds turn on, and then you start to get flow through the system, and that flow rate massively ramps up to just under 100 gallons per minute. As I said, you may not always need 900,000 gallons per minute. This may be all you need, especially, it depends on how big your launch pad is, how big the rocket ship is, and so that'll dictate what amount of flow that you need. So here, it doesn't need as much flow, but you can see how there's some transient activity going on through those spray nozzles. If you were to plot the spray for any of those little spray nozzles, you would see a similar phenomenon. But what I want to do is I want to see what's the total flow through the system. This is my surge tank right here. Okay, this is the supply tank at the top of, where'd it go? I don't know where it went. I was looking for Trey's blog again. Well, anyway, you get the picture. And so I've got a really large supply tank. How much flow are we getting through the system? Well, if you focus in on pipe 1, that would give you your total system flow from the supply tank. So if I go back to my graph results window here, I can do a transient pipe result. And so if I go to pipe 1, I can show the flow rate over time. And there's your total flow. So initially, for your first spray nozzles that are turning on, your flow ramps up to 4,000 gallons per minute. And then a few seconds later, it ramps up to 12,000 gallons per minute. And then if you go further, it ramps up to 20,000 gallons per minute. And then finally, your total flow about 36,000 gallons per minute. Now here's the interesting thing. You see that the time scale actually goes backwards to negative time. How can you have that? Well, for aerospace applications, when you're doing a rocket launch sequence, there's T minus, when the countdown begins. So time 0, that's when your rocket starts taking off. So if you go to the analysis menu under the transient control, this is a situation that you would specify a non-zero start time. So rather than starting your simulation at time 0, we're starting at negative 13 seconds. So that's T minus 13, 12, 11, 10. They're doing the countdown for the rocket ship. And so if I move this over here to the side, it's going from negative 13 seconds out to 14 seconds. That's the launch sequence. So what you will see here is before the rocket ship starts launching, this is where we start flooding the pad. Okay, so this is at T minus about 13 seconds, and then down to 5 seconds. And so this is what is used to suppress those sound waves for that particular application. All right, so just a very unique type of fire type of application using AFT Impulse, but in this particular case, we're using it for sound suppression, not necessarily fire protection, but it makes use of the spray discharge nozzles in AFT Impulse. All right, let's see here. I've got a couple of questions that came in, and let's see here. Let me read them real quick to myself. Okay, so the first question is, for surge analysis for fire protection, how do you calculate the opening and closing time for fire protection equipment, such as a gate valve or a deluge valve or an alarm check valve? Well, honestly, your guess is as good as mine, okay? I don't know. And you're going to have to talk to the valve manufacturer to ask them how long it takes to for those valves to open and close over time. So you'll have to talk with your valve manufacturer. Maybe there's actuators that dictate how long they should take. But the thing that you can really take advantage of with AFT Impulse is you can tune how long it takes and the profile. And so, this is where you may not know how long it takes to open this valve, and neither does your valve manufacturer. So here, this is just a very simple linear opening of this valve. If you got a open percent versus CV table, you can maybe get a little bit more information there. But essentially, if you want, you could do a sensitivity analysis to figure out how long it should take. Should it take this long, or should it take this long? Change the slope of that curve. Maybe you need to change the CV values, etc. And so we don't have any guidance for how long it takes to determine your opening and closing time frames for your surge suppression equipment. That's what you'll have to figure out. For valve closures, it's a lot more exciting, because if you're doing a valve closure where you're closing it linearly like this, what you're going to see is, if you're looking at the pressure at the valve, your pressure is going to stay the same for quite a while, and then it's not going to start changing until right before your valve closes, then it skyrockets. Okay, so the slope of this curve will dictate how high those pressures get to be. The time that you close, if you close over a longer period of time. If you watch one of my previously done webinars that I've done before on surge suppression, you'll see a valve closure example where instead of closing it linearly, you close it part of the way really quickly, and then the rest of the way over a longer period of time. That's what we call, or that's the 80-20 rule. And so, it's all about tuning your valve to figure out how you need to tune it in order to dampen out those surges that you would see. So, sorry that we don't have better guidance for general, guidance on that, but it's up to you. And so you might have to do some sensitivity analysis there. Another question that came in a building that has too many apartments, what is the percent of deluge that you would have to assume that a fire at the same time in order to close to choose the pump? That's another thing that you're going to have to figure out for your design. Basically, the question was, if I can restate it and understand it correctly, is when you're in, if you're in Fathom right here, how do you know how many spray nozzles you're going to need to have turned on at any given time? How big of a pump do you really need? Do you have every single spray nozzle on at the same time to where you would need to have a discharge pressure of 330 psig? You don't know. You have to do an analysis to figure that out. Now, the way that you can do that is by doing scenarios. So you would use the scenario manager, and in the scenario manager, what you would do is different cases where maybe you only flow through these spray nozzles. So what you do is you would basically, take all these spray nozzles and you would shut them off. So if I select these spray nozzles right here like this, and then oops, I don't want to run it. Cancel that. I would close those. So this is how you'd be able to figure out what pump that you would actually need, because you may not have a fire all throughout the whole building. And so you're going to have to do an analysis to figure that out on your own. I know that you're loving my answers on, how do you do this? And the answer is you've got to figure it out. but we've got your back. And so let me show you one more thing on our website, and then we'll close out for the day. So if you go to our website, aft.com, there's consulting hours that we offer when you need some extra help. So if you go to products and then you go down to AFT Flow Expert Package, this is off-the-shelf consulting hours that you can purchase from us if you want us to, take a second look at your model, make sure you've used the right assumptions, make sure that you've, we can double check your input and your modeling choices, and make sure you've modeled things properly. And so when it's just a very quick look, then our Flow Expert Package can work well for you. That way we can go beyond the scope of technical support, and we can help you with your design of your system. Tech support, we can't help you with your design. Okay, that's your design. You have to figure that out as an engineer. But if you need some help designing your system, the Flow Expert Package can maybe assist you with that. Or something that's better might be our sister company, Purple Mountain Technology Group. So if you go to pmtechgroup.com, Purple Mountain Technology Group is our sister company, and they provide consulting services, and they are also experts in our software. And so if you need a lot more detailed help with your specific design for your system, and you need help to figure out how long should it take for you to operate your valves, or how do you figure out what parts of your building might need flow or not, you can contract out to PMTG, and they'll be able to help you on a much more detailed level with your design applications. And so those are two different ways that we can help provide support beyond tech support when it comes to giving you guidance and advice for the actual design of your system. Okay, that is all I had for today. I want to thank you all very much for your time and for listening in. If you have any questions, please do not hesitate to contact us. You can email us at sales@aft.com, or if you have tech support questions, email support@aft.com. You can email me personally at benkeiser@aft.com. That's BENKEISER@aft.com. Thank you all very much for your time today. I hope that you all have a wonderful rest of your week.